Hi, everybody. My name's Kevin Sigwart. I'm the Director of Solutions at OneSpatial Inc. Uh, I'm, I'm pretty sure a lot of the people on this conference call probably knows who OneSpatial is, but for those who do not know who OneSpatial is, we are a data management company where we focus on data management solutions, dealing with data validation, integrating systems, and so forth. And some of our key market areas that we work in is in the Department of Transportation. So we work with a lot of state DOTs. We work in the federal level at federal highways. And then we're also working in a lot of state GIS offices. And as we're working with these different organizations, I'm sitting through a lot of these meetings with these different clients, and we're hearing about some of the challenges that some of the DOTs are facing and some of the state offices are facing, and we're seeing that through collaboration, we and those entities can really help each other on solving some of those problems. And what we're going to really focus in on today is more on the road centerline data sets that these different agencies are maintaining. So at the state level, you typically are seeing state agencies have some sort of statewide network that they're planning on using for NextGen 911, or they're at least in the process of implementing that. And then you also have, at the DOT level, you have state DOTs that are managing data they're managing their assets on their routes. Now, these two data sets are typically operating in a siloed environment, and it makes sense why these are actually happening in a siloed environment. They have different purposes. So at the NextGen 911 level, the data is being used for doing call and dispatch routing. So the way that the network is built is to support being able to send a police car or an ambulance through the network. So in order to support that, it needs attribution that is such as like the information about the street name, address ranges, whatever else you need in there to support that geocoding and that routing piece of it. And to do so, a lot of organizations are implementing the NENA standard for NextGen 911. So there's this schema that they're all trying to conform to that has all that rich attribution information in there. Now, to support these NextGen 911 networks, the locals, so either the counties or the municipalities, are supporting building out, editing those road changes, and supporting out this statewide network. But because we mentioned before about doing this call and dispatch routing, the data sets have to be built in a way to support these systems that they're getting integrated into. And these systems are your CAD systems or your computer-aided dispatch systems. So a lot of these systems, all the systems will require the center lines to be split at intersections. So you will, in order for a vehicle to know that it needs to turn at a specific road, there needs to be a split at that intersection. But what we're also finding is that in these systems, the intersections have to be represented in a certain way in order to support the dispatch. So some dispatch systems require what we call pinch points. And for those of you that are familiar with NextGen 911 routes, you'll see a pinch point looks like almost like a sausage link going through. And I'll show an example of this later. And as I mentioned before, the sole purpose of this NextGen 911 network is to be a routable, or one of the main purposes is for it to be a routable network. And then also as part of the NENA standard, or the NENA standard, is that they want the data to be at a horizontal accuracy of somewhere in the order of 13 feet. Plus or minus 13 feet. And we're finding in a lot of rural areas that it's not meeting that particular standard. So NextGen, these networks are going to have to get their data updated to meet that horizontal accuracy. Now, if we flip over to the state DOT, as I mentioned before, their main purpose is for maintaining these networks, for maintaining their assets on their routes. So they're storing the data in a LRS, or a linear reference system. And basically, I mean, I'm sure most of you know what an LRS, or a linear reference system, is, but basically you have a route that may extend from one end of the state to the other end of the state, and then you build events on on that route based off of what they have, what we call measured values. So the between mile marker 1.6 and 6.5, it is of this pavement type, things like that. And one of the purposes of one of the main purposes of maintaining the data sets like this is to support HPMS, and HPMS is the Highway Performance Management System that is a federal highways initiative. So in order for the federal highways to apportion out funds, they use HPMS to ensure that the data is to ensure what type of assets you have and how much mileage you have of those two particular assets. But as part of that, there's also a piece called Arnold, which is the All Roads Network. And in order to support Arnold, the state DOTs need to be able to get all those local roads and that local information. So now we're starting to see that there could be information that the NextGen 911 network has that the state DOT may be interested in. But when we start getting into some more what's complex about this is that the state DOTs, they're going to be modeling their intersections differently. So they typically model it in what we call like a hashtag. They're also not going to be split at intersections because it's a route. It's going to extend from one end of the state to another end of the state. But we're also finding that because these state DOTs are managing the data for an LRS, they have a lot of connectivity issues. In the past, you're not trying to route on a state DOT network, so it may not have proper connectivity. But on the flip side is that it actually does have, it's actually a very highly accurate data set because a lot of the assets that are being managed on it have survey quality data. So the organizations that are managing the NextGen 911 network may be interested in the state DOT's accuracy to help realign the NextGen 911 network. So you have these two data sets, and there's this relationship that can be formed to help facilitate to meeting some of these requirements that either one of these networks has. So there's many different opportunities, obviously, for collaboration, but three of the ones that we're seeing come up a lot are helping support Arnold. So in order for the DOTs to support that all roads network, they want to be able to get the local updates. Well, one way to get the local updates is to pull it from the NextGen 911 because the locals are already submitting data up to the states for that NextGen 911. So why not grab that data and look to see what's different between what the state DOT has and what the locals have. But also on the flip side is that the state DOTs can help support the state offices on updating their horizontal accuracy. If the state DOT has survey grade assets, why not use that information to update the horizontal accuracy for the NextGen 911? And then lastly, I know that at Federal Highways are also interested in having a more connected network. And in order to do that, you have to have, your routes have to connect at the state lines, but not only do they have to connect to the state lines, they also have to be connected inside the state itself. So being able to align these routes could be something that's of interest to the DOT, and we already know that the NextGen 911 network is a routable network, so they could actually leverage that information to help facilitate that need. So there's obviously this need to do these collaborations, but as we said before, we have we have these two siloed environments. So how do we facilitate this collaboration? And we can do that by trying to connect these data sources together. Now, one solution is to this idea of a one Centerline solution. Now, the benefit of the one Centerline solution is that you have a reduction of duplicate efforts. So maybe you have your LRS and you try to map the NextGen 911 network onto your LRS by building events. At a high level, it makes sense, but when you start digging into it a little deeper, you start to realize that there's a lot of issues with a solution such as this. One is that the route network that's built in the LRS is going to be of a completely different schema than the NextGen 911. If you're trying to manage the NextGen 911 schema and a NENA standard, the LRS may not support that schema. A lot of times the LRS has been developed already before this NENA standard has come through, so the schemas have never been matched together anyway. Also, the LRS is not meant to be a routable network, so it's going to be different in general. Even if you split the events at intersections, but how do you handle when there's a change in PSAP or when there's a change in ESN boundaries? All of that also needs to be accounted for. And then probably the biggest sticking point is, will that LRS network even feed into the CAD system? And if your CAD system requires to have a certain representation for intersections, it won't work. We also noticed that some CAD systems, the digitized direction of the center lines matter for how it does the routing. And the LRS may be digitized to support their measured values. So if they're not digitized in the right direction, that's also going to run into issues. So there's lots of different issues based off of just the spatial information and the attribution, but we haven't even gotten to the data governance section of this. Well, who's going to own this database and who's going to maintain it? So there's lots of issues with a solution like this. And what we're finding is actually that organizations are trying to think of a slightly better solution where they can manage two separate databases, but just provide a mechanism to keep these data sets in sync. And so what you're seeing here, this solution is already a similar solution is already being implemented in Arizona. And I know that organizations such as Kansas and Massachusetts and I'm sure other ones, I'm drawing a blank right now, are also interested in a similar type of solution. And this kind of, it's definitely a little more complex than having one database, but it will help solve some of those problems of the data governance, and also solve problems of how do you ingest a next-gen 911 network into a CAD system and so forth. And basically how it works, how this solution works, is that the locals can submit data to a validation as a service hosted by the state agencies. And a lot of times this may be in the state GIS office. And they can validate their data, get back the results, and then they can address those results at the local level. And we understand that a lot of the locals may not have sophisticated software, so we got to try to make this process as easy as possible. So being able to drive those locals to those issues so that they can fix them, so that that data can then be fed to either the next-gen 911 network or the DOT's LRS network. So then once the locals are doing that validation piece, the next is the change detection side of things. So in order to do the change detection, what is a simpler implementation is to do the change detection of the locals data to the next-gen 911 network. And what we find is that the local network is typically maintained in a very similar, at least a very similar spatial representation as the next-gen 911 network. The schemas could be slightly different because maybe the locals haven't adopted the NINA standard, but then that could be a simple schema mapping exercise. But then once you do that schema mapping, you can then perform that change detection on very similar spatial data sets. So when you perform that change detection, you're looking at more of a vintage over vintage change detection. And then those change detections get fed into what we call change proposals. So the change proposals will identify what changed, what type of change it is. It will drive the users to those changes, and then they can determine whether they want to accept or reject those proposals. So once they determine which proposals they're going to accept and reject, they can then be either automatically fed into one of the systems, so we can automatically feed it into the next-gen 911 network, and then likely those proposals can also be submitted to the DOT to update their data sets in order maybe to support Arnold. They want to get all those new roads that have been added. But some of these proposals can also be subsetted out for the DOT, because maybe if there's an address change, the DOT may not care about the address change. So you can have a subset of those proposals that only the DOT is interested in. Now, typically at the DOT level, they may be leveraging some sort of LRS-based technology like Esri Roads and Highways. So they want to use those tools to actually submit those changes. So instead of automating the process of pushing those changes in, they can just look at those proposals and either trace over the proposals or do some sort of copying and pasting into the DOT's data set, leveraging those tools that is provided. Now, for all of this to work, for this workflow to all work, these two data sets at least need to be synced one time, because if there's information that's in the next-gen 911 network that is not in the DOT network and vice versa, when you do the changes, you're never going to get those changes into either one of these data sets. So by performing a one-time change detection sync between these two data sets, you can at least address all of those changes. And then it's probably a good practice to also continuing to do that check every so often. But you don't necessarily need to do it, on a weekly basis. It's more like something like a yearly basis. Just kind of go back and check those differences between those two. So what I'm going to do now is I'm going to break these down into components, and I'm just going to show you examples of different organizations that we're working with and how they have implemented. And all these organizations, the organizations I'm going to show you have implemented leveraging some of OneSpatial's technology suite for doing validation and integration and change detection. So the first thing we're going to focus in on is the validation piece. So grabbing some of the data that's coming from the locals, validating the data to make sure that it's going to meet the business needs of the next-gen 911 network, but then also the DOT network. So having these rules in place so that that data set can be used in either one. So what we're going to do is we're going to flip over to do a live demo. And I'm going to come into, and now imagine that I am a local. I work in a county or a local municipality, and I'm going to be submitting my data up to the state. But before I want to submit the data up to the state, I want to validate it to make sure that it's going to meet the business needs. So the state can host this application, and this is the One Integrate Data Gateway solution, where the user can log in. It will authenticate them and then give out the rules that their data needs to conform to. That's configured to their needs. So we're going to go ahead and just grab a data set and just drag it in to do that validation. So it's going to upload my data in order for me to run those validation checks. And just so you can see what we're looking at here, we're looking at a road Centerline data set that is at a county. And this is some of the rules that we're going to be running are the exact rules that we're running at in the state of Arizona. So I'm going to go ahead and now that the data has been uploaded, I'm going to run my rules. So we're running 3 different sets of rules here. We're running my essential geometry checks, some validations against the Centerline, and some address validation checks. And these validation checks are going to help support either the next-gen 911 or the DOT's needs for that particular data set. So for example, the essential geometry checks, we're going to make sure that we don't have digitization issues like kinks in the network, like kickbacks or spikes. We're making sure we don't have duplicate features, things that are going to cause issues when we're trying to do the change detection and the integration piece. Then we also have Centerline validation checks that are what maybe the DOT is interested in, and some address validations. So as the locals submit their data up, they're going to be able to get results back in a very timely manner, so they can see exactly what the quality of their data is based off of the conformance to these rules. So if we're looking at some of the address checks, we notice that we don't have any address ranges that are null, but we do have some address ranges that are 0. We have some address ranges that overlap and some gaps. We also have some issues with my Centerline data set. And if I look at my essential geometry checks, it's failing some of the essential geometry checks too. But we want to also provide the locals with the ability to update the data set. So instead of just telling them that they have issues with their data, provide a way or a mechanism for them to update the data. And to do so, we can let them download the report, which is going to pinpoint on a map exactly where the data sets or where these issues are occurring. And in doing so, we're going to provide the data in the format that they submitted in. So if they submit a file geodatabase, they may be leveraging some sort of Esri, or they're likely leveraging Esri technology. So we can give them back that file geodatabase so they can open that up in their in ArcMap or ArcGIS Pro. But say they are a organization that is using some other technology, maybe they're going to upload a shapefile, so we can give them back a shapefile. Or maybe they're using computer-aided drafting data like an AutoCAD. Well, they can upload that AutoCAD file and get back that AutoCAD file. So when we download those results, we can then view those in their viewer, their mapping application of choice. So here we have the road Centerline data set that you just saw that I uploaded. We downloaded those results and we brought them into my ArcGIS Pro application, and I can pinpoint on the map where all my issues are occurring. And just to highlight some of these issues that we located, we found issues with the street name, and I can't see the street name because it's not labeled, so let me go ahead and turn my label on. So in this case here, we're flagging the issue with the road Centerline, and the road Centerline has a name of unknown. If we look at the attribution here, we can see that my Centerline name is unknown, which is why it's being flagged as that nonconformance. We have an example of a duplicate vertice. And if I look at my geometry of this segment, we have two vertices that are the exact same vertex. So this can cause issues, especially if you're trying to build an LRS and you want to add measure values. If you have two vertices in the same location, it can wreak havoc inside your LRS. So you want to make sure you identify those and update those. Connectivity issues, so looking to make sure that we have proper connectivity. This is important for the next gen 911 area. We want to make sure that we have a routable network. So here we're identifying that we have an undershoot based off of a specific tolerance. We also have here, let's see, I thought we had an overshoot. Oh, well, we have an overshoot and an issue with the connectivity. Then we have a bifurcation. So basically what a bifurcation is where you have three segments that are meeting that either have the same route ID or the same road information. Why this is important, this is more important at the DOT level, because if they're trying to generate some sort of, if they're trying to generate an LRS, they need to know which way the measure values go. So you want to have separate route IDs for either one of these, and how you develop the route ID may be based off of some attribution that's in the data set. So identifying where we have three segments meeting with the same row name and then flagging that. And then when we get to the address issues, here we're flagging because we have an address range that has 0 values. So my low and my high addresses are 0. Or if we have an overlapping address range, here we have 2 road segments and the address ranges are exactly the same. And then we also have, here's another example where we have overlapping addresses. And in this case, it's overlapping at the left low and high, 155, 155. So both of these are overlapping, so we're flagging that. So what we were able to do is we're able to provide a way for the locals to come in and update those data sets in order to be ready to go into the integration piece. It can be, we have proper connectivity, we have the proper attribution, it's passing all those validation checks to support that. But as the state's hosting this application, it's also important to state to get a picture of, are the data providers actually using the system? And then not only are they using the system, are they also updating their data? So how is the performance or how is the conformance levels changing over time? And to do that, we can record those metrics in a dashboard. So as those users are submitting data, we're getting the metrics on each individual data provider. So we could see what the total number of conformance levels are. We can see how those conformances are changing over time. We can look at it by individual organization or individual provider, or we can look at all the providers as a whole. We can look at it by individual rules. So if we notice that there's a particular rule that seems to be failing at an alarmingly high rate, maybe we need to do some additional education out to those locals, or maybe there's something wrong with the rule. So in this case here, we have an issue where we have a lot of issues with the Centerline not being split at the intersections. So there's some connectivity issues going on there that needs to be addressed. And then we can just slice and dice the data a little bit more, see an additional example of viewing how the trend is over time. So in this case, this particular provider, they're obviously editing their data, and it seems like it may be getting a little bit better, but obviously back here is when it was the best. Now, all of this is sitting on top of OneSpatial's One Integrated technology, which I mentioned before is a rules-based engine where it's configurable. So you can choose which rules you want to provide to your end users by using a configurable interface. And that is this One Integrated technology. And basically the way it's broken up is it's broken into sessions, which is what was happening when I was running that particular data set. When I hit that play button, it started playing through the session, opening the data up and validating it against a set of validation rules, giving you performance levels. And that can be configured by first choosing what data stores you're using. So what type of data are you connecting to? What's the schema of the data? And so forth. Rules are what you're using to identify the conformance levels, and then actions are what you're doing with the data if it doesn't conform to a rule. So if we take a look at an example at this particular data store here, we can notice that we're connecting to a file geodatabase. We're bringing in the schema. Now, we know that different providers may be representing the data slightly differently, or they may have different schemas. So what we can do is we can re-represent what the data is going to be in the rules, so we don't have to write 1,000 rules for every single organization. We can write one set of rules, and then we can just do the schema mapping on the fly to put in however way we want to represent it in the rules engine itself. If we go back to the input details, so if you're dealing with those flat files that data providers are submitting, you can work with flat files like Esri file geodatabases, shape files. But then say you have data that's already at the organizational level that is in some sort of enterprise database, we can connect directly to those enterprise geodatabases, those Esri enterprise geodatabases, SDE databases, or we can connect to some of those native spatial types like SQL Server, Oracle, and Postgres. Just real quick, let's just show you an example of a rule that we ran on the data set. So here's just an example of the rules and how configurable they are. So in this case, we're saying that we have a Centerline layer. We could choose which feature class we want to validate against if you had, because you could have multiple feature classes. Which field I want to check against. In this case, I'm saying it's not equal to null. But we can also build on this. Maybe we want to say what the street name is equal to a concatenation of multiple fields. So we can actually build the rule to be as complex as the data requires. So maybe we'll come in here. We have a, let's see. We'll do the pre-type plus a space plus the street name. And then you can build that out to be whatever you're trying to do. Is that this would be like the full name would be equal to this set of checks. But we can do more than just checking attribution. We can also do spatial checks. So this is where we're checking to see that two center lines are not overlapping each other. Or we can make it as complex as we need to. Maybe we want to look at the attribution and the geometry. So here's an example of looking for those bifurcations, where we're saying there should only be one other segment where it's intersecting another segment where the street name, pre-direction, and pre-type are the same. All right. So now that we've performed those validation checks and we've provided a way for the locals to update their data, we then can move to the change detection step. So now we want to determine what's different between the locals data and the next-gen 911 network. And to do so, we can leverage the same One Integrated technology to do that change detection and doing it in a rules-based approach. So let me just show what we're dealing with first. So basically here we have two different data sets, two different vintages of data. We have a 2018 data set and a 2019 data set. And I want to perform the change detection between these two vintages of data. Now, the 2018 data set may already exist, well, will likely already exist at the state level's enterprise GIS database. So we want the local just to submit up their updated data and then perform that change detection against what they have at the state level. So to do so, we can do the same thing. We can leverage the data gateway again. Now I'm going to access a different project. Let me log in again. And then this time I'm going to upload my data set. And it's going to, so in this case, we're just going to upload that updated data set, and then we're going to do the change detection between those two, between what is at the state level and what is at the county level. I mean, I'm sorry, what is at the state level and what is at the local provider level. So in doing the change detection, basically the way that we address it is, in this case, because we're looking at vintage over vintage, we can just see, are the geometries the same? If the geometries are the same and the attribution, let me fire this off before I explain what's going on. If the geometry is the same and the attribution's the same, we know it's an exact match. If they're slightly different, we can then determine why are they different and what's the cause of the difference. Is it just an attribution change? Is it some sort of split and is it a split? Is it a merge? Is it have they reshaped the center line? What have they done? And then we can provide after we do that change detection, we can provide a set of proposals. These are all the proposed changes that are between the state data set and the locals data set. Now, depending on how you have your data governance set up, the review process could either be somebody at the state level or at the local level. That just depends on how you are implementing it, and every state is slightly different. So we get that proposal data set, and then we can upload that into my application of choice, and that will show where all of my changes are. So I have adds, deletes, extensions, reshapes. We have scalar changes. Basically, a scalar change is an attribution change. And then we also have things that have been a scalar and an attribution and a geometric change. So like if you're splitting a segment, you probably are also updating the address ranges. So you're going to have a scalar and a split. And inside the proposals, we're giving the user information on what type of change is occurring. So is it a geometric change? Has the street name changed? Has the address changed? What is that particular change? So then the user can open up their application of choice, zoom to the issue, and then determine if they want to accept or reject it. So in this case here, we're identifying that we have an ad. So let's take a look at what this ad's about. So if I look at the 2018 data set, it didn't have this road. And then when I updated it, it now has this road. And it's like it looks like it's some sort of ramp. Well, maybe I'm saying, oh, you know what? At the state level, we are not concerned about that change. So I'm just going to go ahead and reject that change. And then I'm going to go and move on to my next change. And now in this case here, we have an ad. And maybe this time I want to accept it. So we'll go ahead and just accept that. And then we have here we have an example of a delete. So if I look at my data sets, we have the 2018 vintage, and then in the 2019 vintage, that segment has been deleted. So I'm going to say, okay, well, I want to keep that. So let's go ahead and accept. And then we have what we have a partial reshape. So what is a partial reshape? Basically, a partial reshape is when only part of the geometry has changed. So we have this segment here. Let's look at the segment a little bit more in detail. So we have a segment here, and let's turn off. Let's start with the first segment. So here's the original segment. The updated segment is, it completely aligns with the old segment, but then at a certain point, it spins off and it has been updated. So that's why we're flagging that as a partial reshape, because we've only partially reshaped it. And the second half of the proposal, so that's the first part of the proposal. The second part of the proposal is where we're actually retaining that geometry. So we're going to go ahead and accept both of those. What else do we have here? And then here's another example of a partial reshape. In this case, the road segment was updated to move up here. Well, actually, I don't want that, so I'm going to go ahead and reject that. And then here's another example of a reshape. In this case, the geometry was reshaped because they updated the segment to be aligned to this other segment. Because before, let me turn this off. If we look at the original data set, we could see how the start ends aren't aligned here. So that would have failed one of those validation checks that we originally did. So maybe the locals noticed they had that issue. They updated it now to align so that we are now flagging this geometry as a reshape because they've updated it and they moved both of these geometries. So we're going to go ahead and just accept both of those. And then we're going to go ahead and let's go to this last example here. And here we have a scalar update. And a scalar update is an attribution change. So what type of change is it? Well, it looks like the name changed, but we don't have an address change. So I could take a look. Let's see what those changes are. So if I look at the 2018 vintage, it looks like there was a dash that was in the street name, but that dash was removed. Well, I'm going to say, yeah, we'll go ahead and accept that. And then we can continue through this effort just to go through and address whether we want to accept or reject all of these issues. We can also automatically determine whether we want to accept and reject them also, but a lot of organizations want to at least have a way to review those before those getting pushed into their statewide data set. So once we perform all that, we can go ahead and save those changes, and then use that new data set to integrate it into my network. So what we're going to do, let's flip back over here. So we perform that change detection. We have those proposals. And the next thing we want to do is we want to take those proposals and update our two data sets. Well, for the next gen 911 network, we know that they are a similar they are a similar representation, so we can use an automated workflow to take those proposals that have been accepted and automatically integrate those into the 911 network. But then maybe for the DOT one, we want to manually go ahead and go use the tools themselves to push those changes in. So let's come back and let's log back into my data gateway. This time we are going to do the integration piece. So we're going to go ahead and log in. And I'm going to pull my proposal data set that I've edited, that I've updated. So with all those accept and rejections, and we'll just drag that in. It's going to upload those features. There's only 112 changes, and of those, only a certain subset of those are actually accepted or rejected. And then we're going to go ahead and run it. And basically, we're going to remove all the rejected proposals. So then now we're only down to 83 changes, and we're going to integrate those changes into the statewide data set. And if we come back over here, we could take a look at those results. So in my map now, I have the original 2018 vintage, the updated 2019, and then the updates that were actually pushed in, so the updated network, and that's what the blue line is. So if we come back to some of those examples, well, here was where we had that ad, and I accepted that ad, so we inserted it into the data set. Right here is where we rejected that proposal, so notice we didn't insert that in. Where we had the delete, notice we deleted that street segment because that was an accepted proposal. Where we did that reshape, we notice now we have updated the data set so that it is now reshaped and aligned. Where we had that parcel reshape, we've updated the segment so that it is moved to now align to that new data set. So we updated that proposal to accept that proposal. Here's an example of where we rejected the proposal, so we didn't push that change in. And then where we applied that scalar change. So here we have, we updated the network now, so we got rid of that dash. It's now updated with that street name. Now, if we go to the DOT network, what we may want to just do is we want to subset out to only the types of changes that the DOT is interested in. So things like if they may or may not be interested in the street name change, maybe they are interested in the street name changes. So you can add that type of proposal, but maybe they don't really are interested in address changes. So then they can just go, and same thing as we did before, they can look at those proposals, they can zoom to the issue, they can zoom to that proposal, and then they can use whatever technology of their choice to integrate this into their DOT network. So they can leverage, if they're using Esri roads and highways, they can use that to integrate those results into it. All right. Now to the one-time sync. Now this is the most complicated piece of the puzzle. It's how do you synchronize two data sets that have different representations. They represent intersections differently. One is segmented, and one is a route is a route data set, an LRS data set. Well, we can leverage one integrates change detection rules to facilitate this and help get rid of a lot of those false positives because the networks are slightly different. And to do so, we will, let me see here. So in this case, let me open up my map first to show you what we're looking at. So here we have two different networks. We have the route network, which is a segment, which is not segmented at intersections, we can see here. But then we have the local data set that has been segmented at all the different intersections. So we want to perform a change detection between these two data sets. So we can bring in these two data sets into the one integrated technology. We have rules to do that change detection between an LRS route and a 911 network, and determine what's different between these two, and then use that to synchronize these two data sets. Once we have a synchronization, we then can do other things like conflation type efforts. So if I look at my proposals, anywhere we have a match, so all these silver lines are matches, we can use that to actually help update the network to align to that. So if you want to realign your next-gen 911 network to the DOT network or vice versa, you can do that. Or you can also use this as a way to build events along your network if you're a DOT. So if we take a look at some of these proposals real quick, here's where we're identifying an ad. It wasn't in the state data set, the state DOT, but it was in the 911 network. Here's an example of a delete, so it's just the reverse of that. And then we have an example here where we have an add, and then we have a reshape because that geometry has changed. So we've updated that to be a reshape, and then we have an add. But where this gets a little bit more difficult, a little more complex, is where we start to run into where we have these pinch points, like I mentioned earlier. The 911 network is represented data as in a pinch point. The DOT network is represented data in like a hashtag format. So if we do the change detection just straight up, we're getting a lot of these false positives that are going to have to go through and manually address each and every one of these. And what we want to be able to do is we want to say, well, maybe let's try to account for some of these false positives so it makes the end user easier to do this integration. So to do so, we can identify where we have a pinch point, and let me turn off my proposal, and we can update the data set to represent it like it's represented at the DOT level. Now, in this case, we're doing this all in the application itself. We're not going to be writing any of this out. I'm just writing it out just for the demonstration purposes. So once we explode out that pinch point, we then do the change detection based off of now a like representation of the network, and we're going to get a better matching ratio, based off of using that updated network. So this was an example of one type of pinch point, and then here's a couple other examples. So here we had a three-way intersection. Now, notice how when I re-represented the network, it's not perfect, but it is close enough to do the change detection. We're not trying to get to a perfect update of the pinch point. We're just trying to get it close enough so when we do the change detection, we won't get these false positives. And the same thing, here's an example of a four-way intersection. So when we do the change detection between these two data sets, we're getting matching records, getting rid of those false positives. So once we then do that synchronization and we identify what's matching, we then can either, as I said before, we can build those matching into the LRS, or we can have some sort of matching table that can be used to keep these in sync for the foreseeable future. If there's any differences between those data sets, they can be addressed so that you can push over any updates into the LRS and vice versa. And then you can also say, well, maybe if one of these networks, maybe the DOT cares about certain types of data that the 911 network doesn't care about, and so that those can be just rejected, and then they don't have to worry about that anymore. So by taking that and matching these data sets together, you are helping facilitate these collaboration efforts. So being the DOTs are now able to get the information about what the changes are to support Arnold. If you do the matching piece, you can then update either network to align it to whatever one is of a higher quality network or higher precision network. And then you can also use it to help do some of the edge matching and updating the network too. And I didn't really get into more about how we can do that alignment because we only have an hour. But if you're interested in anything a little bit more detail, I'd be happy to have that conversation with you. So with that, I'm more than happy to answer any questions that anybody may have.